Right now, you are sitting in a quiet room, perhaps feeling safe within the walls of your home, your city, or your country. The Milky Way, a city of stars so vast that a beam of light, traveling at the speed limit of the universe, takes 100,000 years just to cross it. That is longer than the entire history of human civilization. And yet, here's the terrifying truth. On the true map of the universe, our colossal galaxy is nothing more than a ghost, a speck of dust lost in the cosmic web. Tonight, we leave the Earth behind. We will climb the cosmic ladder from our solar neighborhood to the great walls of the universe to discover where we truly fit. Welcome to the epic scale of the Milky Way. When we talk about our galaxy, it helps to picture something simple: a city of stars, vast, bright, organized, and alive with motion. A wide, flat disk with a bright center and long, curved arms. This is the Milky Way, a barred spiral galaxy roughly 100,000 light-years wide, containing somewhere between 100 and 400 billion stars, and weighing about 1 trillion times the mass of the Sun. Seen from above, it would look like a great rotating pinwheel of light, quietly turning through the dark. Its structure is straightforward once you break it down. At the core lies the central bulge, a dense concentration of older stars surrounding a supermassive black hole. Around it stretches the disk, the part that forms the familiar spiral pattern, long arms filled with gas, dust, and active star-forming regions. Enveloping everything is the halo, home to ancient stars and globular clusters that orbit far above and below the disk. And beyond even that is the galaxy's dark matter halo, the invisible framework holding the Milky Way together as it spins. Now, where are we in all this? The Sun sits in a small, modest feature called the Orion Spur, a minor branch between two of the Milky Way's larger arms, Sagittarius and Perseus. We are located about 26,000 light-years from the galactic center, a comfortable distance from the crowded, energetic core. If the galaxy were laid out like a simple map, we'd be about 2/3 of the way from the center to the edge. Not downtown, not the outskirts, but a quiet, balanced region in between. And we're not sitting still. Right now, as you lie here listening, the Sun is orbiting the galactic center at about 220 kilometers per second, nearly 500,000 miles per hour. At that speed, it will take roughly 25 to 250 million years to make one full orbit. One galactic year. Since the first dinosaurs appeared, we've only made one. This position, in a calm, mid-distance region, may be one of the most important factors in Earth's history. Closer to the center, the density of stars increases dramatically. There, radiation is higher, supernova explosions are more frequent, and gravitational chaos is stronger. Conditions like that make it harder for planets to remain stable over billions of years. Farther out, on the other hand, the galaxy becomes too sparse. There are fewer heavy elements, the metals forged by earlier generations of stars. Without those elements, rocky planets like Earth are less likely to form. So our location is not just ordinary, it's fortunate. Astronomers sometimes call it the galactic habitable zone, a wide region where conditions are neither too violent nor too barren for long-term stable planetary systems. It's not a strict boundary, but a useful idea. Life may need the right kind of neighborhood, even on this galactic scale. Humanity understood none of this for most of history. For thousands of years, the Milky Way was simply a faint, milky band across the sky. It wasn't until the 18th and early 20th centuries, through the work of William Herschel and later Harlow Shapley, that we began to map its shape and understand our position within it. Shapley's measurements revealed a humbling truth. The Sun is not at the center of the galaxy. We live far from it, in a quiet region among billions of other stars. But that humility comes with calm, because being away from the busy, dangerous core may have been essential for life to arise and endure on Earth. It gives our solar system the stability it has enjoyed for more than 4 billion years. Stability that allowed oceans to form, continents to shift, and life to emerge and evolve long enough for us to wonder about our place here. So when you imagine the Milky Way tonight, don't think of a chaotic whirl of stars. Think of a structured, balanced home, a broad disk, a glowing center, long sweeping arms, and a quiet neighborhood where our sun drifts in peace. A stable place in a galaxy built on motion. But our galaxy is not drifting through space alone. It lives in a small community, a tiny neighborhood called the local group. If the Milky Way is our home galaxy, then the local group is the small neighborhood surrounding it. The collection of galaxies bound together by gravity, traveling through space as a quiet island in a much larger cosmic sea. The local group spans roughly 10 million light-years, and it contains a little more than 50 galaxies. Most of them are small dwarf systems, faint and irregular. Only 3 stand out as major spirals with real structure: the Milky Way, Andromeda, and Triangulum. The Milky Way is one of the 2 giants here, a barred spiral with hundreds of billions of stars. But the true heavyweight of the local group is Andromeda, also known as M31. It lies about 2.5 million light-years away, and it may contain close to 1 trillion stars, making it the largest galaxy in our neighborhood. It is roughly similar to the Milky Way in shape, but slightly bigger and brighter. The third major member is Triangulum, or M33. It is smaller, perhaps 40 billion stars, but still a fully formed spiral galaxy with its own arms, clusters, and star-forming regions. If the local group had a family photo, these 3 spirals would be the ones in the center frame. Surrounding them, like small satellites orbiting larger worlds, are dozens of dwarf galaxies. The Milky Way alone has a collection of companions: the Large Magellanic Cloud, the Small Magellanic Cloud, the Sagittarius Dwarf Galaxy, and many faint dwarf spheroidals discovered only in the last 2 decades. These satellite galaxies are not just decorative. They are fragments of the local group's long, complicated history. Leftovers from earlier mergers, building blocks consumed by larger galaxies, and reservoirs of gas and stars that continue to shape our own. The Milky Way has grown over billions of years by absorbing galaxies like these. Some of their stars now live in our halo, their orbits stretched and mixed by gravity, leaving behind faint streams, the scars of ancient collisions. But the most important relationship in the local group is the one between the Milky Way and Andromeda. These 2 massive spirals dominate the region, and they are not drifting apart. They are moving toward each other at about 110 kilometers per second, roughly 250,000 miles per hour. It sounds fast, but across a 2.5 million light-year gap, it is a slow, steady approach that will take another 4 to 5 billion years before the 2 galaxies begin to merge. This future collision is not a Hollywood disaster scenario. Galaxies are mostly empty space. Stars will almost never hit each other. What will happen instead is a long gravitational dance. The shapes of both spirals will stretch, twist, and eventually blend into a single, larger system. A new elliptical or lenticular galaxy, already informally called Milky Way. We will return to that story in segment 8, but for now, It's enough to know this. The Milky Way and Andromeda are already on a path toward each other. The future of our local neighborhood is one of slow transformation. Though it contains dozens of galaxies, the local group is not a crowded place. Compared to massive clusters like Virgo or Coma, it is quiet, open, even sparse. Galaxies here are separated by millions of light years, giving each other plenty of room to evolve without constant interference. This lack of density is important. In giant galaxy clusters, there is intense radiation, frequent collisions, and hot intergalactic gas-stripping galaxies of their star-forming material. But in the local group, conditions are calmer. The Milky Way and its companions can move through space largely undisturbed, forming stars at a steady pace. If you travel to the southern hemisphere and look at the night sky, you can see two pale, glowing smudges. Those are the Magellanic Clouds, real galaxies, orbiting ours, visible to the naked eye. They are reminders that our galaxy does not live alone, and that even from Earth, we can glimpse pieces of our galactic neighborhood. The local group itself is not isolated either. It sits on the outer edge of the Virgo supercluster, part of an even larger structure we will explore next. Imagine taking the map you built so far and pulling back until the local group shrinks into a tiny dot. What comes into view is a structure stretching roughly 110 million light-years across. This is the Virgo supercluster, a vast gathering of hundreds of galaxy groups and clusters, including our own. Inside it sits the Virgo cluster, one of the largest concentrations of galaxies in our cosmic neighborhood. Astronomers estimate it contains somewhere between 1,000 and 2,000 galaxies, many of them enormous ellipticals and spirals. Among these giants is M87, a massive elliptical galaxy whose central black hole was the first ever imaged by the Event Horizon Telescope. We won't dive deeply into its details here, but knowing it exists helps you appreciate the scale. The Virgo cluster is like the downtown district of this supercluster, dense, energetic, and packed with heavyweights. By comparison, the local group is a quiet suburb on the outskirts. It orbits gently, far from the crowded central regions where galaxies interact more frequently, and gravitational tides can strip material away. This separation gives the local group room to evolve on its own terms. But even the Virgo supercluster, enormous as it seems, is not the true boundary of our galactic environment. In 2014, astronomers mapping the motions of galaxies discovered something even larger, a structure that redefined our sense of place. They named it Laniakea. The word comes from Hawaiian, Lani meaning heaven, Akea meaning immense, the immense heavens. A fitting name, because Laniakea spans roughly 520 million light-years and contains around 100,000 galaxies. Within this incomprehensibly large volume, the Virgo supercluster is just one component, and the local group is a small tributary feeding into a much larger flow. If the local group is a neighborhood and Virgo is a metropolitan region, then Laniakea is the entire continent, a sweeping landmass shaped by gravity. The defining feature of Laniakea is the way galaxies move inside it. Across hundreds of millions of light-years, galaxy groups, including ours, drift in similar directions, as if following subtle currents in space. Their motions trace pathways that all appear to converge toward the same region. Astronomers call this region the Great Attractor. It sounds dramatic, but we can explain it simply. It's not a single object pulling everything in. It is a gravitational basin created by the combined mass of many clusters, filaments, and dark matter concentrations. Imagine a shallow valley on an enormous landscape. anything nearby naturally rolls toward the deepest part. In that sense, the Milky Way is not sitting still. It is flowing along with thousands of other galaxies, moving toward this gravitational low point at about 600 kilometers per second, roughly 1.3 million miles per hour. But you don't feel it. Our entire cosmic neighborhood is drifting together, carried by the large-scale structure of the universe. This motion is one reason it helps to picture Laniakea, not just as a static cloud of galaxies, but as a dynamic river, where each galaxy is a bright droplet drifting along the same vast current. Among those droplets is our Milky Way, one of 100,000. And that is the mind-bending part. Even a galaxy containing hundreds of billions of stars becomes almost insignificant when placed inside a structure this large. If every galaxy in Laniakea were a grain of sand, the entire local group would fit comfortably in your hand, while Laniakea would stretch like an enormous beach beyond anything you could see in one glance. Yet for all its immensity, Laniakea is still only one piece of the cosmic puzzle. Its boundaries are not walls, but transitions, regions where the flow of galaxies shifts toward neighboring basins. And beyond Laniakea, the universe continues. Filaments, voids, threads of matter, and structures that weave together to form the cosmic web. You can feel the scale changing beneath you, like climbing rungs on a ladder you didn't know existed. Local group, Virgo, Laniakea. Each step reveals that our home galaxy, so enormous on its own terms, is part of a hierarchy far larger than intuition allows. Even Carl Sagan once remarked, almost in passing, that the cosmos is within us, made of star stuff, a reminder that the materials forming our bodies come from processes taking place across all these scales. Understanding where we sit among them deepens that connection without overwhelming it. So as you rest tonight and listen, imagine the Milky Way not only spinning on its own axis, but drifting through Laniakea's gentle gravitational flow, while Laniakea itself moves through an even larger pattern. It's a quiet motion, steady and ancient, carrying our entire galactic home across the deep dark. But even Laniakea is not the whole story. Step back just a little more, and a hidden pattern begins to appear. The cosmic web. When you zoom beyond Laniakea, even its half-billion light-year span begins to fade. Galaxies no longer appear as individual islands. Superclusters no longer appear as giant realms. Instead, new shapes emerge. Long bridges, glowing knots, and enormous empty basins. You are now looking at the cosmic web, the largest structure we know. It helps to imagine stepping back until Laniakea becomes a tiny glimmer on a vast map. All around it, you would see filaments, immense chains of galaxies stretching across hundreds of millions of light years, weaving together like threads of a cosmic fabric. Between these filaments lie enormous voids, places so empty that entire galaxy groups can drift through without encountering a single star. The cosmic web is not a poetic idea. It is a real, measurable structure. Its filaments, nodes, and voids form the skeleton on which the universe has evolved for 13.8 billion years. And our entire home, local group, Virgo, Laniakea, sits on just one small filament within this network. As you pull away from Laniakea, the first thing you notice is how galaxies line up along narrow, elongated paths. Gravity pulls matter together into these strands, while the regions in between remain almost completely empty. This contrast, dense threads and enormous voids, is what gives the cosmic web its shape. Some filaments are famous because of their size, the Sloan Great Wall, the CFA2 Great Wall, the Hercules Corona Borealis Great Wall. You don't need to remember their names. The key idea is simple. These walls are among the largest known structures in the universe, and they are made entirely of galaxies in motion. A filament is like a gravitational highway. Galaxies form, evolve, and flow along these structures, drawn toward larger clusters at the intersections. Our Milky Way belongs to one of the smaller filaments feeding into Laniakea's main basin, a gentle current carrying us through a much larger river of matter. Then there are the voids. These are the vast, silent regions between the filaments, some stretching hundreds of millions of light years across. They contain so few galaxies that if you traveled through them, you could go for unimaginable distances without seeing a single point of starlight. Voids are the reason the cosmic web stands out so clearly. Dense filaments look brighter and more defined when surrounded by these immense spaces of almost total emptiness. They also highlight just how small the Milky Way is, even within its own filament. And now we climb to the highest rung of this ladder, the observable universe, the largest scale science can measure. The observable universe is the region from which light has had time to reach us since the Big Bang, roughly 13.8 billion years ago. Because the universe has expanded during that time, this region is much larger than 13.8 billion light years. Its diameter is about 93 billion light years. Inside this enormous bubble are an estimated 2 trillion galaxies, based on deep observations from the Hubble Ultra-Deep Field and refined by early JWST surveys. 2 trillion. And the Milky Way is just one of them, one galaxy among 2 million. The mind naturally struggles with numbers like this. So here are 2 simple pictures to hold on to. If each galaxy were a grain of sand, then the observable universe would be dozens of Olympic swimming pools filled to the brim. If the Milky Way were a single coin, the observable universe would be the size of an entire continent. Even Laniakea, with its 100,000 galaxies, would be nothing more than a faint patch on that continental map. So now the scale becomes clear. Local group, a few dozen galaxies. Virgo supercluster, hundreds of groups and clusters. Laniakea, 100,000 galaxies. Cosmic web, filaments, hundreds of millions of light years long. Observable universe, 2 trillion galaxies across 93 billion light years. And through all of this, the Milky Way drifts quietly inside its filament, carried along by currents shaped long before Earth existed. As Neil deGrasse Tyson once reflected, the universe has no obligation to make sense to us. Yet here we are, slowly mapping it step by step. But if the universe is so vast, where exactly does our Milky Way rank among its countless galaxies? When you look at the Milky Way from the inside, it feels impossibly large. 100,000 light years across, containing hundreds of billions of stars. But to understand where it truly sits in the universe, we need to compare it with the full spectrum of galaxies that exist. And once we do, a clearer picture appears. The Milky Way is big, but not alone among giants. It belongs near the top, yet far from the very top. Let's begin at the smallest end. Most galaxies in the universe are not majestic spirals or massive ellipticals. More than 80% are dwarf galaxies, small, faint systems containing from a few million to a few billion stars. Their diameters range from 1,000 to 10,000 light years, tiny compared to the Milky Way. Examples include the Fornax dwarf, the Sculptor dwarf, and companions of our own galaxy such as Leo the First and Leo II. Some orbit larger galaxies, slowly being stretched and torn apart by gravity. Others drift alone in the cosmic dark, too small to gather enough gas to form many stars. In sheer numbers, dwarfs dominate the universe. But in size and influence, they sit at the bottom of the ladder. Above the dwarfs are what astronomers often call typical galaxies. These contain tens of billions to a few hundred billion stars, and they commonly span 30,000 to 60,000 light years. Most spirals and lenticular galaxies you would imagine fall into this category. Many are smaller than the Milky Way by a wide margin. If you were to choose a random galaxy from the universe, chances are it would be one of these, neither tiny nor exceptional, but comfortably in the middle. And then there is our galaxy. With a diameter of roughly 100,000 light years, a stellar population between 100 and 400 billion stars, and a dark matter halo giving it a total mass close to 1 trillion solar masses, the Milky Way stands out. Not as a monster, but as a top-tier spiral. By size and mass, it ranks in roughly the top 5% of galaxies in the observable universe. Not the largest, not rare, but undeniably a heavyweight. Its structure also sits at an interesting balance point. Large enough to form generation after generation of stars, yet stable enough to avoid the violent conditions found in the cores of larger clusters. It is big but livable, a combination that turned out well for life on a small planet orbiting an ordinary star. But if you want to see what true galactic extremes look like, you have to meet the giants. Galaxies like IC 1101, stretching nearly 1 million light years across and containing an astonishing 100 trillion stars. Or A2261 BCG, another giant of similar scale. Or EM87, the massive elliptical at the heart of the Virgo cluster, home to one of the most powerful known black holes. These galaxies are often found in dense environments, such as rich clusters, where mergers happen frequently. They are round or oval rather than spiral, because their original structures have been stirred and reshaped over billions of years by repeated collisions. They are extraordinary, but also inhospitable. Star formation is slow or nearly non-existent. Their centers are crowded, energetic, and turbulent. Compared to these titans, the Milky Way suddenly feels modest. But compared to the vast majority of galaxies, it remains enormous. Somewhere very high on the list, but far from the summit. The Milky Way is bigger and more massive than most galaxies ever will be. Yet it is still overshadowed by a class of giants that push galactic scale to its limit. That duality creates a feeling that is both grounding and humbling. Our galaxy is significant, but not supreme. Impressive, but not exceptional. A heavyweight, yes, but one that sits below the cosmic champions. And somewhere in that range lies a quiet truth about perspective. As Shakespeare once wrote, "There are more things in heaven and earth than are dreamt of in our philosophy." The universe is vast enough to hold galaxies of every size, from dwarves barely large enough to shine, to giants so massive they bend our sense of scale. But size alone doesn't make a galaxy friendly. Some galaxies are so extreme that life as we know it could never survive there. When you look across the universe, the Milky Way seems familiar. A quiet spiral, slowly rotating, forming stars at a steady pace. But step back and survey the full variety of galaxies out there, and you'll notice something striking. Most galaxies are far more chaotic, more extreme, and far less friendly to life. Astronomers sometimes call this diversity the galaxy zoo, a reminder that the universe builds galaxies in many different shapes and temperaments. Spiral galaxies are the ones we know best. They have a flat disk, curved arms, and active star-forming regions. The Milky Way is one of them. Andromeda is another. These galaxies are balanced, not too violent, not too quiet, with ongoing star formation and enough heavy elements to create rocky planets. They're common, but not the only design nature uses. Elliptical galaxies look different. They are round or oval, lacking spiral arms, and filled with older stars. Most of their gas has already been consumed or blown away, so new stars rarely form. The largest galaxies in the universe, like IC 1101, stretching nearly 1 million light-years across, are ellipticals. M87, with its enormous central black hole, is another famous example. These galaxies are impressive, but not welcoming. Their cores are crowded, energetic, and bathed in radiation. They contain fewer metals, the elements needed to build Earth-like worlds. For life, they are harsh environments. Some galaxies don't fit any tidy category at all. Irregular galaxies have no clear structure. They are often the result of gravitational encounters, mergers, or close passes with larger galaxies. Their stars, gas, and dust are arranged in unpredictable patterns, as if they were torn apart and left to drift. They remind us that galaxies evolve through collisions and interactions, not calm isolation. Then there are the starburst galaxies, places where star formation runs wild. While the Milky Way forms maybe 1 or 2 new stars a year, starburst galaxies can create hundreds. This activity floods the galaxy with intense ultraviolet radiation, powerful winds, and frequent supernovae. It sounds spectacular, but it's terrible for stability. The environment changes too quickly. Stars live short, turbulent lives. Planetary systems struggle to survive long enough for life to develop. If the Milky Way were a starburst galaxy, Earth would never have had billions of years of quiet evolution. Some galaxies contain active galactic nuclei, AGN for short. These are powered by supermassive black holes consuming matter at a rapid rate. As gas falls toward the black hole, it heats up and emits enormous amounts of energy, outshining the entire galaxy. Many AGN launch jets that extend millions of light-years into space. If Earth were anywhere near one of these cosmic searchlights, our skies would be filled with lethal radiation. Stable atmospheres and long-term life would be impossible. AGN galaxies are spectacular to observe and completely unsuitable for living worlds. Now, when you return your attention to the Milky Way, its quietness makes more sense. Our galaxy has no powerful AGN, no starburst regions producing stars at frantic speed, no giant cluster environment stripping gas away, no catastrophic level of radiation, and a steady star formation rate that has persisted for billions of years. Its spiral arms move smoothly. Its central black hole is relatively quiet. Its position in the local group is peaceful, with plenty of room to evolve without constant collisions. This calm is why a small planet orbiting a modest star could remain stable for billions of years, long enough for oceans to form, continents to shift, and life to slowly emerge. In other words, the Milky Way is big enough to be rich in heavy elements, but calm enough to allow long-term habitability. It's a rare balance, a combination that many galaxies do not offer. The universe is filled with extremes. Galaxies ripped apart by gravity, galaxies blazing with newborn stars, galaxies lit by jets that stretch across intergalactic space. Against that backdrop, the Milky Way's gentle nature becomes something to appreciate, even to be grateful for. It's like Brian Cox once said, "In the grand cosmic drama, our galaxy plays a quiet role, and that's a blessing. A quiet galaxy gives life time to breathe." But this calm galaxy wasn't always calm. It was built through ancient collisions, and it's heading toward another one. When you look up at the Milky Way on a clear night, it's easy to imagine it as a quiet, ageless structure, a galaxy that has always been the way it is now. But in reality, the Milky Way is the product of a long, dynamic, and sometimes violent past. It was built through collisions and mergers stretching back to the earliest moments of the cosmos. And billions of years from now, it will enter the next great chapter of its evolution, a slow-motion encounter with Andromeda. Let's start at the beginning. The early universe, shortly after the Big Bang, was surprisingly smooth. There were no galaxies yet, no stars, no planets, just a hot, expanding sea of particles. But this smoothness wasn't perfect. There were tiny variations in density, small wrinkles in the cosmic fabric. Those wrinkles were amplified by dark matter, an invisible form of matter that outweighs the ordinary matter we see. Dark matter began to clump under its own gravity, forming the first dark matter halos, invisible wells that would later become the birthplaces of galaxies. Gas flowed into these halos, cooled and collapsed. The first stars ignited, and from these scattered sparks, the earliest proto-galaxies emerged, small, rough, and chaotic. Galaxies did not form in one step. They grew by merging. Small galaxies collided and combined to form larger ones. Those merged again, creating even larger systems. This process, called hierarchical assembly, is the primary way galaxies build themselves. The Milky Way is no exception. Over billions of years, it has absorbed numerous dwarf galaxies, each one adding stars, gas, and dark matter. Astronomers can still see the evidence. Streams of stars in the halo trace the remnants of ancient mergers. The Sagittarius dwarf galaxy is currently being torn apart and stretched into long arcs of stars. Another major merger, known as Gaia Enceladus, happened about 10 billion years ago and left behind a distinct population of stars with unusual orbits and chemistry. Even the halo structure, its shape, density, and motion, tells the story of galaxies long gone, their identities dissolved into the Milky Way's growing form. After billions of years of growth, the Milky Way has reached a relatively stable phase. It is no longer merging with large galaxies, and the most dramatic interactions of its past are long over. Only small satellite galaxies remain, like the Magellanic Clouds, slowly spiraling inward, contributing fresh gas and stars. The Milky Way is, in many ways, an adult galaxy, still evolving, still forming stars, but past the most chaotic stages of its youth. But its story is far from over. Andromeda, the nearest large spiral galaxy, sits about 5 million light-years away. It is moving toward us at roughly 110 kilometers per second, a slow, steady drift that will eventually bring the two galaxies together. The first close pass will begin in about 4.5 to 5 billion years. By then, the Sun will be nearing the end of its life. But for the galaxy itself, this will mark the beginning of a long, graceful transformation. Despite the dramatic name, galaxy collisions are not like physical crashes. Stars are incredibly far apart. Even when two galaxies overlap, the chance of two stars hitting each other is effectively zero. But gravity still reshapes everything. As the Milky Way and Andromeda approach, their spiral arms will distort. Gas clouds will compress, triggering bursts of new star formation. The central regions may flare with activity as material flows toward the supermassive black holes at each core over several billion years. The two galaxies will pass through each other multiple times, gradually losing their distinct shapes. Eventually, they will settle into a single, larger structure. likely an elliptical galaxy, already nicknamed Milky Way. It won't be a sudden transformation. It will be a long, slow process, unfolding over cosmic time. The solar system might survive the merger entirely. It could remain intact, simply following a new orbit within the combined galaxy. Or it might be flung outward toward the galactic outskirts, moving into a quieter, more distant region. But by then, the sun will be aging into a red giant, and Earth's conditions will be dramatically different. The galaxy's reshaping will matter little to life on our planet, because the timescales of stellar evolution will dominate our fate long before the merger reaches its peak. It's easy to imagine galaxy collisions as chaotic or destructive, but the reality is gentler. Galaxies merge the way rivers join, gradually, naturally, shaped by gravity and time. There is beauty in the process, not danger. Knowing this removes the fear and leaves only awe. A galaxy is not a fragile thing. It evolves, it absorbs, it reshapes itself. And the Milky Way is part of that ancient cycle. As one cosmic thinker once put it, in every merger, the universe reshapes itself, and so do we. It's a reminder that change, even on the grandest scales, is a natural part of the cosmos. The Milky Way has grown through billions of years of collisions. And billions of years from now, it will join with Andromeda to form something new. A quiet galaxy today, but one built from ancient fire and heading toward another chapter in its long, drifting story. But our quiet local group is not like the crowded galaxy clusters that dominate the universe. And that difference changes everything. When you zoom out from the Milky Way, past its spiral arms, past its dark matter halo, past the empty stretches between it and Andromeda, you eventually see the shape of our immediate cosmic neighborhood. The local group looks peaceful from this distance, almost like a small island floating in a dark ocean. It contains a little over 50 galaxies, most of them tiny dwarfs, loosely gathered around three anchors: the Milky Way, Andromeda, and the Triangulum Galaxy. There is space between these systems, huge distances that keep interactions slow, gentle, and rare. For a galaxy, this is the equivalent of living in a quiet suburb. A place where nothing too violent happens, a place where the night sky can stay calm for billions of years. But the universe isn't made only of neighborhoods like ours. There are also the cosmic megacities, the galaxy clusters. If the local group is a small town near the edge of a great continent, then a galaxy cluster is a skyline of skyscrapers rising from a dense electric core. The Virgo cluster, one of the closest large clusters, packs 1,000 to 2,000 galaxies into a region only a few tens of millions of light years across. Where we have generous space between galaxies, Virgo has crowding. Where our galaxies drift quietly, theirs weave through a busy environment shaped by enormous gravity. Inside clusters like Virgo, galaxies interact constantly. They swing past each other, tugging on star streams and warping their shapes. Gas is stripped from smaller galaxies as they plunge through the superheated plasma that fills the cluster, a process called ram pressure stripping. That plasma itself glows fiercely in X-rays, a signature of temperatures reaching tens of millions of degrees. Star formation can stall, flare, or collapse entirely depending on these conditions. Even basic features like spiral arms can be shredded. In places like that, galaxies live hard lives, and stable long-term environments, the kind life requires, are far harder to maintain. This is the contrast that matters. The Milky Way doesn't live in a chaotic high-rise district. It lives far outside the bustling core of Laniakea. Our local group sits on the outskirts, where gravitational tides are weaker, where interactions are slower, and where a galaxy can hold on to its gas without fear of being stripped bare. The Milky Way has had billions of years to form stars steadily, quietly, predictably, conditions that allowed the sun to exist and the Earth to remain calm long enough for life to try again and again. Imagine for a moment an alternate universe where the Milky Way formed deep inside a cluster like Virgo. Our galaxy would face regular gravitational harassment. It might lose much of the cool gas needed for star formation, and the solar system, if it ever formed at all, could experience far more frequent disturbances from passing giants or surges of high-energy radiation. In such a place, the night sky might be spectacular, full of bright nearby galaxies. But spectacular does not mean safe. The quiet patch of space we occupy today may have been one of the few where complex life had the uninterrupted time it needed to evolve. That's why this suburb of the universe matters. The local group isn't glamorous. It isn't crowded. It doesn't have the towering ellipticals or wild starburst galaxies that headline the cosmic news. But what it does have is stability. A long, steady stretch of peaceful cosmic weather. And that quiet, almost boring backdrop is the reason someone like you can lie back on a bed in the dark, breathing slowly, listening to a calm narrator describe the universe, instead of living under a sky full of violent radiation storms. There's a gentle wisdom in the idea that sometimes the safest place in a storm is not the center of the city, but a quiet house on the edge of town. In cosmic terms, that house is the local group. And our galaxy, tucked safely between its neighbors, drifting in a tranquil corner of space, has been sheltered long enough to grow life, memory, thought, music, stories, and curiosity. And that curiosity leads naturally to the next question. The one humans have been asking for as long as we've looked up at the stars. If our galaxy sits in such a favorable place, and if there are billions of stars nearby, then where is everybody? When you look up at the night sky, it's easy to feel small. But the numbers behind those points of light are so large that they almost break language. Astronomers estimate that the observable universe, the part of the cosmos where light has had enough time to reach us, contains roughly 2 trillion galaxies. And if an average galaxy holds around 100 billion stars, then the universe is home to something like 200 billion trillion stars. It's a number so large that your mind can't hold it. But it's the right starting point for a question that humans have carried for decades. With all these stars, where is everybody? Before we get to that, it helps to step gently through what we've learned in just the past 30 years. When NASA launched the Kepler Space Telescope, astronomers expected to find planets only around a few stars. Instead, they discovered that planets are the rule, not the exception. Many stars have systems of planets. Many of those planets are rocky, and many orbit in what scientists call the habitable zone, the region where temperatures might allow liquid water. It means that worlds like Earth are not rare jewels. They are common outcomes of star formation. And that simple finding changes the entire conversation, because once you know planets are everywhere, a basic probability argument naturally appears. You don't need equations for it. Just imagine that among all those stars, only a small fraction have Earth-like planets. Only a small fraction of those develop simple life. Only a small fraction of those ever evolve intelligent beings. And only a small fraction of those build technology. Even if every step is extremely rare, even if each layer reduces the number by orders of magnitude, The universe is so large that the final count could still be enormous. Hundreds, thousands, millions, maybe more. And yet, we have no clear evidence of anyone else. This tension between the scale of the universe and the silence we observe is what physicist Enrico Fermi pointed out during an ordinary lunch conversation in the 1950s. He simply asked, "Where is everybody?" The question became known as the Fermi paradox, the puzzle formed by a universe filled with stars and planets, and the striking absence of any sign of other technological civilizations. People have suggested many possible answers over the years, but they tend to fall into a few gentle themes. None of them sci-fi, none of them dramatic, and all of them grounded in simple reasoning. One idea is that life itself may be rare. The leap from chemistry to biology could be incredibly difficult, so difficult that it may happen only a handful of times in an entire galaxy. Another possibility is that intelligent life is rare. It took Earth nearly 4 billion years to produce a species capable of building radios and telescopes. And that path may be unusually fragile. Some scientists think civilizations may simply not last very long. They might burn through resources, disrupt their ecosystems, or create technologies they cannot control. Others point out that the universe is incredibly wide and incredibly quiet. Signals weaken quickly, distances are enormous, and civilizations might not overlap in time. One may rise and vanish millions of years before another begins listening. There is also the humbling possibility that we may be early, among the first civilizations to appear, simply because the universe is still young. Most stars that will ever exist have not yet been born. In that sense, our silence may not be surprising. The great conversation of the cosmos may not have started yet. And finally, it's possible we are not listening very well at all. Our entire radio civilization has lasted only a few decades, a blink compared to the 13.8 billion year age of the universe. We have sent only a handful of deliberate signals. We have scanned only a tiny percentage of the sky in a narrow set of frequencies, with instruments that are primitive compared to what future generations will build. If the universe is broadcasting, we may have barely lifted the antenna. But the most interesting part of all of this is not what we don't know. It's what we do know about our own galaxy. The Milky Way alone contains hundreds of billions of stars. Many have planets. Many of those planets are small, rocky, and warm. And within that vast collection of potential homes, life has already appeared at least once. On a world orbiting an ordinary star, in a quiet spiral arm, inside a peaceful corner of a modest galaxy. The universe has succeeded in producing chemistry that can ask questions. We are the data point that proves the probability is not zero. We are the experiment that worked. Whether we are alone or surrounded by quiet neighbors we have yet to detect, the fact that life emerged here, on a pale blue world drifting through a calm galaxy, is extraordinary. The silence of the universe may say nothing about its emptiness. It may reflect only the infancy of our tools, the vastness of the distances, or the possibility that we are early participants in a long, unfolding story. Arthur C. Clarke once wrote, "Two possibilities exist. Either we are alone in the universe or we are not. Both are equally terrifying." He meant it as a reflection on humility, a reminder that whatever the truth is, it will reshape our understanding of who we are. And that brings us to the next step of our journey. Because even this staggering cosmos, filled with trillions of galaxies and uncountable stars, may not represent the whole story. What we call the observable universe might just be the part we can see from our cosmic address. When we talk about the universe, we often imagine the entire thing. Every galaxy, every cluster, every stretch of space. But what astronomers call the observable universe is not the whole universe. It is simply the region of space where light has had enough time to reach us since the Big Bang. Everything we see, every galaxy photographed by Hubble or James Webb, sits inside that glowing bubble of visibility. A helpful way to imagine it is to picture yourself standing on the deck of a ship at night. Your eyes can only see as far as the horizon allows. Beyond that horizon, the ocean doesn't end. Your vision does. The observable universe works the same way. It's not a boundary of the cosmos. It's a boundary of what light has been able to deliver to us. This limit exists because light travels at a finite speed. The universe has been around for about 13.8 billion years, and even though space has expanded along the way, there's still a maximum distance light can cover in that time, forming a sphere around us about 46 billion light-years in radius. That makes the observable universe roughly 93 billion light-years across. Enormous, vast, almost unthinkable. But here's the twist. That entire sphere may be nothing more than our cosmic horizon, the farthest line we can see, not the farthest line that exists. Beyond that distance, the light simply hasn't arrived yet. And so there is every reason to believe the universe stretches farther, much farther. Cosmologists often compare this to standing on a wide plain. No matter how far you look, the horizon curves away. You can walk toward it forever, but you'll never reach the end. The plain might be finite or infinite. You can't tell from where you're standing. In the same way, the observable universe tells us nothing certain about the true size of the universe. It tells us only how far its story has reached our eyes. What makes this even more profound is the physics of cosmic inflation, the nearly instantaneous expansion of space in the earliest fraction of a second after the Big Bang. According to inflation theory, the entire universe ballooned outward so quickly that most of it is now forever beyond our reach. Not because it doesn't exist, but because light from those distant regions will never have time to reach us, no matter how long we wait. In this picture, the observable universe is like one tiny patch sewn onto a quilt whose edges stretch far beyond the room, far beyond the building, far beyond any distance you could walk in a lifetime. The quilt itself might be unimaginably large, possibly infinite. Some versions of inflation even suggest that the universe may contain many such patches, each with its own horizon, its own galaxies, its own physics shaped during its own moment of expansion. Scientists sometimes call this idea the multiverse, not in the fantasy sense of alternate realities or magical worlds, but simply as a natural consequence of the mathematics behind space expanding at different rates in different regions. It is important to say this carefully. The multiverse is not proven. It is a possibility suggested by some theories, not an observation. But it is one of the most fascinating ways physics challenges our sense of scale. Even if the multiverse never becomes more than a hypothesis, the essential point remains the same. What we can see may be a tiny fraction of what exists. The cosmos may extend far beyond our horizon, so far that the Milky Way, the local group, Laniakea, and the entire cosmic web occupy a region smaller than a drop of water in an ocean without shores. And yet, in all of that vastness, this tiny patch, our patch, is the only one we know where matter has arranged itself into thinking creatures who can wonder about the rest. The observable universe provides us with the only canvas we can study, the only stars we can count, the only galaxies we can map. But the larger universe, if it exists, reminds us that mystery is built into the structure of reality itself. Thinking about this doesn't need to make you feel lost. If anything, it often creates the opposite feeling, a gentle awe, the kind that slows your breath and softens your thoughts. It reminds you that the part you can see is beautiful, intricate, and full of story, and that beyond it lies something even grander, something too large to grasp, something still unfolding. Carl Sagan once wrote, "We are a way for the cosmos to know itself." And that line holds even more weight when you consider that we are conscious inside just one shimmering bubble of visibility. Out there may be countless more bubbles, countless more galaxies, countless more places where nature experiments with light and matter. The separation between what we can see and what might exist sets the stage for a final shift in our journey. Because once you recognize that we are tiny, smaller than small, in a universe that might exceed every boundary we can imagine, the next question becomes deeply human. What does that smallness mean for us? For our lives? For our sense of belonging? The scale keeps growing outward, but meaning always pulls inward. So, what does it mean to be a tiny, thinking creature in a galaxy that's both huge and small at the same time? For most of human history, we told a simple story about our place in the cosmos. The Earth sat at the center of everything. The sun and stars revolved around us. The heavens were a dome, and we were the main characters living beneath it. That story didn't last long. Slowly, step by step, the universe peeled away the layers of our confidence. First, we learned that the Earth moves around the sun. Then we learned that the sun is just one star among many. Then we discovered that the Milky Way is not the entire universe, but only one galaxy among billions. And finally, we saw that even our galaxy, with all its stars and worlds, is just a single swirl in a cosmic structure too large for words. Each revelation pushed us farther from the imagined center. And for a long time, that felt like a loss, as if the universe were stripping away our importance. But distance brings clarity, and over time, a different feeling emerged. The universe wasn't shrinking us. It was showing us the full picture. When you see Earth from a modest distance, just a tiny sphere wrapped in blue light, something unexpected happens. You don't feel smaller. You feel connected. You feel part of something that stretches far beyond your own lifetime. And the more we learned about our galaxy and the cosmos around it, the more this shift in perspective took root. Because if you follow the chain all the way down, from cosmic webs to superclusters, to galaxies, to stars, to atoms, you eventually arrive at something familiar. The matter in your own body. The carbon in your muscles, the oxygen in your lungs, the calcium in your bones, all of it was forged in ancient stars. Your brain, the thing thinking these thoughts right now, is arranged from atoms that once floated through interstellar clouds. You are literally made of the same material that built the Milky Way. Brian Cox says it simply: we are the cosmos made conscious. And whether you're lying in bed, sitting on a porch, or listening in a quiet room, that sentence is not poetry. It's chemistry, it's physics, it's history. It means that the universe is not something happening out there at a distance. Part of it is happening in you. A fragment of the cosmos has learned to look back, to question, to wonder, to dream, That changes the meaning of smallness. Because in a universe this large, being the center was never the point. Understanding was. The Milky Way, in this new frame, is not just a structure of stars and dust. It is a home in the deepest sense. Everything humans have ever done, every story told, every problem solved, every moment of laughter, every piece of music, every discovery, every goodbye, happened inside this one spiral galaxy. Every ancestor you've ever had lived under the same faint band of light across the sky. Among trillions of galaxies, the Milky Way is the one that holds the story of you. And for all we know, it may be one of the few places where the universe has learned to think. When you carry that gently, the scale of the cosmos no longer feels overwhelming. It feels grounding. It shows you that significance doesn't come from size. It comes from experience, from the ability to feel, to remember, to love, to create meaning in a world that doesn't impose any by force. The universe will not hand us purpose, but it gives us time, a small window between two eternities. And in that window, on a tiny world in a quiet spiral arm, life has learned to open its eyes. So what does our small place really mean? It means we don't need to be the center to matter. It means we don't need to control the universe to feel at home in it. It means that existing, even briefly, even quietly, is its own extraordinary privilege. Every thought you have tonight is something the Milky Way has never done before. It's new. It's fragile. It's part of the universe's long, patient way of knowing itself. And now that we've traveled from atoms to galaxies, to the edge of the observable universe and beyond, we can finally let the story return home. To a quiet arm of the Milky Way, where the stars keep their slow watch. Now, with all of that in mind, let's return home, back to our quiet arm of the Milky Way, and let the universe keep watch while you rest. You've traveled a long way tonight, farther than any spacecraft, farther than any telescope could ever take you. And now, as we begin to drift back home, the universe gently folds itself into something softer, something quieter. Think of the journey we've just taken, from the small place where you're lying now, out into the spiral arms of the Milky Way, past the local group, through Virgo, across the great sweep of Laniakea, along the threads of the cosmic web, all the way to the edge of the observable universe, and then beyond, into the possibility that the cosmos may stretch without end. And now, we're simply coming home. Let everything slow down. Let the scale shrink gently, like the tide drawing itself back from the shore. The cosmic web, with its vast filaments, fades into the background. Laniakea drifts past like a cloud of distant light. The local group appears again, that small island of galaxies where we belong, and the Milky Way rises slowly into view. A soft, glowing swirl turning in the dark. See it not as a machine of stars, but as something almost dreamlike, a silver mist with a heartbeat billions of years old. A place that has been steady for longer than life has existed on Earth. A place that will continue its slow rotation long after tonight ends. Now we drift closer toward the Orion Spur, toward the quiet lane where the sun makes its long orbit around the galactic center. The sun has circled the Milky Way more than 20 times since it was born. And still, tonight, it shines with the same gentle steadiness it has always offered. A small star, but enough to warm a world and support every life that has ever lived. Let the view narrow a little more. The planets appear, tiny beads around a single point of light. and among them, a blue one, a fragile, glowing whisper wrapped in a thin breath of air. Earth, your home, your one place in this vast structure, every memory you carry, every voice you've loved, every joy, every loss, every discovery humankind has ever known, has taken place on this small blue dot drifting quietly in the dark. And tonight, from where you are, that little world is safe. Now bring the picture closer. Past the continents and oceans, past the swirls of clouds, down through the atmosphere, into the familiar shapes of the world you know. Until finally, the journey returns to your room. The small space where you're lying now. Nothing vast, nothing cosmic, just the comfort of a bed holding your weight, the steady darkness around you, and the quiet air settling gently in your lungs. Let your shoulders release just a little. Let the muscles around your eyes relax. Let your breath fall into a slow, natural rhythm. The universe doesn't need anything from you tonight. It doesn't ask you to solve it, understand it, or carry it. It has moved through 8 billion years without your help, and it will continue turning while you sleep. All you need to do now is rest. You are in a calm galaxy, in a quiet neighborhood, on a gentle world, in a dark room that asks nothing of you except to breathe. For small creatures such as we, the vastness is bearable only through love. Carl Sagan said that, and on nights like this, it feels true. Because the vastness isn't here to frighten you. It's here to make your own small space feel peaceful, like a warm cabin surrounded by endless mountains. You're exactly where you need to be. Safe, still, weightless in your own quiet corner of the Milky Way. So let the galaxy turn on its own tonight. Let the universe drift as it always has. And let yourself drift too. You are safe, and the night is quiet. Good night.